So I want to talk about domain and range a little bit today. I got another assignment I'm putting up. Might even get two up there. Yeah, they're really short. They don't take very long to do. That's good news for you guys. Okay, so what we want to do today, we want to click those close, please, all the way close. So we want to talk about domain and range when it comes to graphs. You've already done an assignment where you had to identify domain and range from tables, right? Was that on the first assignment? Was a little bit, okay. So maybe the second assignment. So you've had a little practice with that. That's not a big deal. What we want to look at today is finding domain and range when you're given a graph. So you're going to, and we're going to do a lot of that stuff in this unit, which is pretty easy stuff. There's really no algebra to do. It's just inspecting a graph and getting information from the graph, right? Quick review. We're moving from, this is how we would have written this equation up until now this year, right? But when we start to talk about functions, we're going to trade the y notation for the f of x notation. A lot of times we do this kind of thing with, with functions that mean something. Like if we're going to calculate the surface area of a sphere, for example. Well, we know that surface area is a function of radius. Now think what that means. It means I should be able to input values of the radius and output from the function the surface area of the sphere, values for surface area. Right? And we do that with an equation. We've got some function. If we square the radius and then multiply it by 4 pi, that's how we calculate surface area, right? So we could combine these things. Yeah, we know surface area is a function of radius, and this is the rule that we use. F of r is equal to 4 pi r squared. But what we do a lot of times in math is instead of making those separate things, we just write it like this. We write S of r because the S has some meaning. S stands for surface area. So this is telling us surface area as a function of radius. In other words, we're calculating surface area by picking values of radius, right? And this is what we do to those values of radius. That's the rule that we use to calculate surface area, okay? All right, so we can skip that. We've done that stuff. Here's a way to kind of think about functions then, and domains and ranges. Now, we already said that domains and ranges, domain is the set. We talked about this, I think, last week, maybe earlier this week. We talked about domain is the set of all the input values, usually x values for us, right? The range is the set of all the output values, usually the y values, right? And so you can think about a function as like a machine, right? It's like you're producing something for a company or for a industry, where the domain is what contains all the raw materials that go into the function machine. You feed those into the function machine, and it does its thing, and it spits out a finished product, which is the values of the function. We collect those in a different warehouse that we call the range, right? So these are just holding areas for the input raw materials and the output product from the function machine, okay? So when we talk about domains and ranges, then we need to be able to communicate what they are. There's 3 ways we do that in math. One way is using inequalities. You're very familiar with that, right? Like how would we say this in math? How would we read that mathematically?
2 is less than x.
Yeah, but we always start with the x, right? If it's a compound inequality. So try it again. X is
greater than 2 and less or equal than 6.
good. So x is greater than 2 and less than or equal to 6. That gives us a pretty good visual picture of what the domain is, right? It's all the x values between 2 and 6, including 6, right? That's one way to say it. We can just use inequalities. That's something we've been doing for a while. We reviewed that at the start of the year. There's another method that we're not going to use, and that's called set notation. Notice that set notation, it's really the same thing, isn't it? All we did was we just said, okay, we're going to enclose this in brackets, which means it's a set of values. So this just says the set of values of x such that x is greater than 2 and less than or equal to 6. That's very redundant, right? There's really no reason. To me, we're not going to use that way. You might see it in college, you might not, but it's another way we could do it. But we're not going to mess with it because it doesn't really give us any additional information from this way, right? It's implied that we're talking about x because that's an x, right? So we don't need to have all this other fancy stuff in there. Now the third way is a way that we will use also. So we'll use methods 1 and 3. This is using interval notation. Now interval notation communicates the very same thing. So these two statements are exactly the same. They're just being said in different ways. When you use interval notation, here are the rules for it. The smallest number always goes on the left, and the larger number always goes on the right, just like a number line. Just exactly like we do with a compound inequality, right? Notice that the 2 is on the left, the 2 is on the left. 6 is on the right, 6 is on the right, okay? We use different grouping symbols to communicate whether or not we're including the endpoints. Now, the 2 is not included, right? Everybody agree? The 2 is not included, and so we give it a rounded grouping symbol, like a parenthesis, right? The 6 is included, and so we give that a squared off bracket. There's an easy way to remember that. It takes more ink to draw the bracket, just like it takes more ink to draw the equal sign under the inequality, right? So it takes more ink to do all the stuff that requires more ink. And if we were to think of this in terms of, if we were to graph that interval on the x-axis, what would that look like? So if that's the x-axis, and that's 2, and that's 6, how would I graph that inequality? Think back to our review at the start of the year. Remember that, Jace? What kind of an endpoint would we put there? Open circle there, very good, and here we put closed circle, and then we're just going to take everything in between, right? So once again, it's consistent, right? It takes more ink to draw the closed circle, it takes more ink to draw the bracket, it takes more ink to draw the line, okay? So it all goes together. I don't care if you know this vocabulary or not, honestly, but we would say that this kind of a situation where you're using parentheses where we're not including endpoints, we call that exclusive. We're excluding the endpoints. If we use the brackets, so we're including the endpoints, we call it inclusive. And something like this we call semi-inclusive. Semi just means half, right? So it's half inclusive and half exclusive. I don't care if you know that. That's really not a big deal. Just know how to use this stuff. Okay, so let's get a little practice with it. But one last thing. So most of this is, I'm not going to spend a lot of time on this. I'm sure this makes sense. We already did some of this. We already did the compound inequalities. Let's take a quick look at something like this. What if we want to, if the domain is like all values of x greater than 4 or something like that, right? How do we say that? Well, it's pretty easy to do with an inequality. We just say x is greater than 4. A just stands for some number, right? What if x is less than or equal to some number? Then we just say that. That's no big deal. How do we say that, though, with interval notation? This is a little weird, but does this make sense that that's how we'd say it with interval notation? Think what this graph would look like. We'd have an open circle down here at A, and then we would just go to the right forever. So there is a bottom limit to that, isn't there? Right? There's a left boundary, a bottom boundary, which is at A. But is there a top boundary? No, there's not. So how do we say that there's no top boundary if we're using interval notation? With interval notation, we have to put something on the left and something on the right. Well, the something we put on the right to indicate that there is no upper limit is infinity, right? Because infinity, after all, is not a number. You can't ever get to infinity. It's just out there forever, right? So does that make sense? Okay, and then if we wanted to say something like x is less than or equal to a, well then notice that we're going to have the square bracket for our upper limit. But to the left, there is no bottom limit. We would just say negative infinity, meaning we could go all the way from whatever a is, call it 4. We're going to go all the way down through all the negative numbers forever and ever. It never stops, right, towards negative infinity. Could we ever put a square bracket on an infinity symbol? I mean, would that make sense? Would something like this ever make sense? Does that make sense? What do you think? Somebody be brave. How come? You're right. How come? Well, he was brave. So he said no, and have somebody defend his position for him. What? Yeah, it means it includes it, right? Can you include infinity? No, it's not a number, right? You can't ever get there, so it would make no sense to put a bracket on the end, right? Wouldn't make any sense. How do you suppose you could say, what if the domain was all real numbers? How would we say that? If our domain all real numbers, how could we say that? How about let's start with interval notation. How could I say that using intervals? What could I put on the left and the right if there's no boundary? Infinities, yeah. On the right, I'm gonna put a positive infinity. On the left, I'm gonna put a negative infinity, and I have to have rounded brackets. Think what that says. This is all numbers, all the way from negative infinity up to positive infinity. Well, that's everything, right? So that's one way of saying all reals. We could also say all reals is just, did we do this at the start of the year? Were there somewhere you had to put in that script R? Seems like there were, right? So that's just a symbol for all real numbers. I think you can do that again on some of these, or maybe I even let you put in just an R for all reals. I can't remember, but there's some ways you can do some little shortcuts like that. But the other way you could do it is if you were writing this using inequalities, you could just say x is greater than negative infinity, and less than positive infinity, and that's yet another way of saying everything, right? Okay, so let's practice a little bit. Let's find domains and ranges. So what about the domain of this function? Now, the domain is the set of what kinds of values? X values, right, the inputs. Okay, so there's some stuff that's kind of implied here. I could understand why you'd be a little bit unclear about what the answer should be. Why don't you take an educated guess? What do you think the domain is going to be here? I mean, it's going to be a set of values, right? But then let's go ahead and let's do it using inequality notation. How about first? So x is what? Say it again. The domain. Now here's another way to think about that, right? It's the set of all the possible input values. Another way you could think about it is if an ant were going to walk along this function, if that's its universe, right? What are all the possible x values, the x coordinates that the ant could have as it walks along the function? So for example, if the ant is right there, whoops. If the ant is right here, it's at the point x is 8 and y is 10. So its x coordinate would be 8. Could its x coordinate be 7.9 if it took a step? Sure, could, right? Could it be 0? Well, yeah, right there it is, right? Right there the x coordinate is 0. Could it be negative 10? Well, I mean, you think it could? Yeah, because there's nothing to tell us that this ever stops, is there? Right? This is just a random picture of this graph. We just chose some kind of arbitrary window to view this thing, but if I zoomed out, presumably I'm going to see this thing continue doing what it's doing there, right? If I zoom out, it'll just keep going up and to the left over here and to the right over there. So presumably it could be at 10 somewhere. What do you think?
I'm just confused when it's 0 for x.
Oh, that's not 0, that's 4, isn't it? Whoops. Yeah, no wonder. Okay, I was looking at the wrong thing there. So that's going to be, right, that's going to be an x value of 4. Here would be an x value of 0. I don't know what the y value is there, but there's an x value of 0, right? Could we get to negative 10? Yeah. Is there any limit to what the x values could be if I zoomed out far enough? So what do you think the domain is? All reals. Right, so the domain is all reals. Another way of saying that, negative infinity to infinity. There's another way to think about the domain. Right, the domain is the set of all the x values. So there's kind of a little game you can play in your head to help you see from a function what the domain is. Imagine that we took this entire function and we squished it down onto the x-axis. What would the mark on the x-axis be? I mean, if I took the whole function, which goes forever, and I squeeze it onto the x-axis, wouldn't it end up looking like just the entire x-axis? Right? So once again, it's all reals. Okay? How about something like that? What's the domain there? Now this is just a small picture of the function, right? What's it, if I were to zoom out, what's the function going to do to the left, do you think? Keep going, right? Keep going. So we could indicate that. I guess we could just draw a little arrow there and say it keeps going. What's it going to do if I zoom out if the ant's walking to the right? just keeps going up, but he can always go up and to the right. Everybody agree? So what's the domain for this one? Yeah, the domain would be all reals. Okay. What about the range? Let's look at the range. The range is the set of what values? Y values. Okay, so the range is the set of Y values. To think about the set of Y values, you almost have to tilt your head sideways, right? What's the positive Y direction? Well, up, right? Y is a vertical variable, so that's going to be the positive Y direction. That's the negative Y direction, right? So what do you think? What's the range of this thing? How could I, if I want to do kind of an analogous thing to what I did with squeezing the function onto the x-axis, with the range, where would I squeeze the function? Yeah, I'd take the whole thing and just compress it onto the y-axis. Now, what kind of a mark would it leave on the y-axis if I did that? I mean, it's going to go up forever, agreed? Where's it going to stop, though, vertically? Like what's the lowest value it could get to? -1. Okay, so that's the question, is what do we do at -1? So that's, if I squeeze it onto the y-axis, it looks like that. Do we include the -1 or not? And I wouldn't expect you to know the answer. Does somebody want to hazard a guess? No, how come? Just a guess, okay. So I'll tell you the answer, and you gotta really, this is gonna kind of blow your mind a little bit here. This is, the red line, this isn't part of the function. This is what we call an asymptote. Now, an asymptote in math means a line that you approach more and more closely but never get to. Okay, so it's like this. Think about this scenario here. So every second for the rest of eternity, I am going to cut my distance to the door in half. You'll never get there. Aha, I'll never get there, will I? Even if we let this experiment run forever, do I ever get to the door? No, I don't. But here's the weird thing. If I take an infinitely fine Sharpie, is there any pen, or is there any mark I could make on the floor that I wouldn't eventually step on? If I can't make the mark on the door, I have to make the mark on the floor, so it can't be on the wood, right? Is there any mark I could make on the floor that I wouldn't eventually step on? Yeah, I could? How am I gonna do that?
Put it over here, something like.
Well, okay, but no, I'm saying a mark, okay, a mark between here and there. Right, so in other words, could I make a mark so close to the door that I wouldn't step on it?
No.
No. And maybe you're thinking, well, what if just make one right next to the door? Make one on the point next to the door. Is there such thing as a point next to the door? There isn't, right? Because if I just zoom in closer, how many points are between that one point that you thought was next to the door? How many points actually exist between that point and the door? Well, more than that. An infinite, right? If I can zoom in infinitely far, there's no limit to how many points I can expose between that point and the door. So you think, oh, okay, well, I zoomed in. I'll just pick the one that's next to the door now. Now just zoom in again. There's an infinity more points there, right? So isn't that weird? I never get to the door, but any point between me and the door, I'm guaranteed to step on eventually. As soon as I make a mark on it, all I have to do is keep stepping and I'll eventually get there, right? That's a weird concept, isn't it? Right? So what would you say in math we would call the limit of my motion?
The range.
What's the point that we would call the limit of my motion? So what's the boundary, in other words? Well, I mean, it's related to that, but what's going to be the boundary of my motion? What's the thing that I'm always approaching? The door. So even though I never get to the door is clearly that's the limit of my motion, right? We can identify that that's the thing I'm approaching, we just never get to, right? Same thing's happening with this function here. As the function sweeps down to the left, it's just going to hug that asymptote more and more closely, but it never gets there. So what do you think? Do I need an open circle or a closed circle? I need an open circle, right? And so what's my range look like then? If I write it using interval notation, what's it going to look like? So what's the lower limit, lower y value? -1. What's the upper y value? Infinity. And what kind of symbols do I need? What do I need there? I need parentheses because it's not included, right? And then I always have to have a parenthesis up there. So if I write that using an inequality, I would just say y is what? Greater than -1. Bear with me? Okay. How about this? What's the domain of that function? Six and, so what do you mean? Tell me what to write, Carson.
6 and
-4 and, okay, but we're talking about domain. Is that x or y values? X values, okay. So 3 would be my lower boundary. 9 is my upper boundary, right? And I could write that if I'm writing domain. How am I going to, what am I going to do with those? What goes here? Parentheses, because look, that's not included, right? If the ant walks along this function, he can get as close as he wants to x equals 3, but if he actually steps on x equals 3, he falls through a wormhole or something, I don't know. He just disappears, right? Because the function isn't defined there, right? So we have to put a rounded bracket there, but x equals 9 is included, so that would have to be square, right? Or we could say x is greater than 3 and less than or equal to 9. What about the range? So the range is a set of y values. Okay, what's the upper boundary? -4. Do I include that one? Can he ever actually stand on a y value of -4? Yeah, he can, right there, right? At that point right there, his coordinates are x equals 6, y equals -4, right? So if I smush that onto the y-axis, I've got a closed circle there. What's my lower boundary? -7? -7. What kind of boundary do I put there? Katie, what do you think? Just ask yourself the question, can he have a y value of -7? Is there a place he could stand on that function and have a y coordinate of -7? Well, he couldn't there, but what about there? Okay, he could, couldn't he, right? So it doesn't really matter that that one's open because this one is closed, so he can't stand there. So I'd have a closed circle, and that's my range, right? So my range would look like -7 on the bottom, -4 on the top. Or I could write it as y, whoops, I forgot, I had wrong brackets, didn't I? So y is greater than or equal to -7 and less than or equal to -4. How about that? What's the domain there? What's the domain there? What's the lower limit of the domain, Cooper? It's my bottom boundary on the domain. That's the x values, right? Say it again?
-7.
That, well, now, I'm looking at, this is the x-axis, right? So we're talking domain or the x values, so the horizontal values. -8 is the furthest left I can go on the function, right?
Yep.
But I can't stand there, so that's gonna be open circle. What's the furthest right I could go? 4, and that is included, isn't it? So that's my domain. So -8 up to +4 would be my domain. What about the range? What do you think about the range here? So -7 looks like the lowest point, doesn't it?
Yeah.
And then there's, the ant could walk all the way up to +3. Everybody see that? So my range would be, and those would both be included, wouldn't they? Okay, you get the idea? Okay, it's not so bad, is it? Okay. I think we're okay. What's the range of that one real quick? What is it? To positive infinity, right? Good, so it's all reals. Good. range of that one, we did one like that. I think we're good. So last thing, average rate of change, and then we're done. I'll give you guys a work day on Monday too, how's that? So finding the average rate of change of a function. So average rate of change, here's all it is. The average rate of change is just the change in the output divided by the change in the input. That's it. Okay, change in the output, which is the change in y values if it's on the xy plane, if it's a graph. And the change in the input would be the change in x if it's on the xy plane, so if we're graphing it, right? So it describes how an output quantity changes relative to the value of the input quantity. It doesn't really matter what happens in between. It's only what happens between those ending values. If you drive to Hermiston, which is 30 miles away, let's say, and for some reason it takes you an hour to get there, what's your average speed?
30 miles an hour.
30 miles an hour. Okay, that's an average. That's what we're talking about. That's an average rate of change. That really is your average rate of change of position. It would be 30 miles per hour. Does that mean that you're going 30 miles an hour the whole time? No, not at all. All kinds of strange stuff can happen between when you start and when you get there. But we don't care about that. We're talking about an average rate of change. All we care about is, what's the final value of the time, what's the final value of the distance, what happened from endpoint to endpoint. That's it. Okay, so if we want to make a calculation like this, if we want to calculate the average rate of change in gasoline price from 2005 to 2012, what's going to be my input here? This is giving us cost of gasoline for years, for the year. So here's our function. C must stand for cost, right? Y stands for year. So which is the input variable? Y, right? The function notation tells us that, right? So that's the input value. Cost is the output value. If we want to calculate the average rate of change, all we have to do is take the final output value, which is this, right? This minus that, right? The final value minus the starting value. If we do that, 3.68 minus 2.31 is 1.37, right? So that's the change in the output. What's the change in the input? Well, 2012 minus 2005 is just 7. So if we divide that, we get about roughly 20 cents per year is how much it increased. Why did it increase? Because the final value was higher than the starting value. What if the final value had been 131? It'd be nice, wouldn't it? The final value was 131. Then we would have taken the final value of 131 minus 231 would have given us negative $1. Divided by 7 would have given us, 14 point something cents, right? So we would have had a negative rate of change, which would have meant something because that would have meant that it was decreasing, right? The cost of gas was decreasing. Here it's positive because it was increasing. The final value was bigger than the starting value. If we look at this on a graph, it's really simple though, right? If we want to find the rate of change from negative 7, which is right here, up to x equals positive 7, which is right here, well, look what we can do. What are the coordinates on the graph? We got negative 7 is my x value, 2 is my y value. Right here we've got positive 7 is my x value, negative 2 is my y value. So all we have to do is make the calculation from the ordered pairs, right? The average rate of change is just going to be the change in y over the change in x. Change in y always means it's always the final value minus the initial value. So our final value for y was negative 2. Our initial value was positive 2. Divided by our final x value is 7 minus our initial x value is negative 7. So what's that give us? Negative 2 minus 2 is negative 4. 7 minus negative 7 is 14, so we get negative 2/7. It probably shouldn't be surprising that if we draw a slope triangle from this point to this point, we rise by negative 4 and we run by 14. Isn't that what we got right there? Just rise over run. Right? So you can also think, if you're talking about a graph, the average rate of change is just the slope of the line that connects the points. We call that in math a secant line. So it's the slope of the secant line, the line connecting the 2 points, the starting point and the ending point, and that's it. What would we get, real quick, in this last one? What would we get on this one here if we calculate the average rate of change from x equals 0. Well, there's the point on the graph when x is 0, right? All the way up to x equals 6. Well, there's the point on the graph when x equals 6. Tell me real quick, what's the rate of change? What'd you say? 0. How come? Because the line is a horizontal line. What's the slope of a horizontal line? 0. Yeah. So the rate of change is 0 in that case. Okay? All right. How much time you got? Well, that's better than nothing. You can work a little bit. I'll give you Monday as a work day. How's that? I'm going to update grades.